The Immortal property, how commutativity became the superhero of the matrix multiverse. In the ever-changing world of linear algebra, where matrices transform and shift through different bases, this one property stands unshakable. In our problem today, A23, we're tasked with showing that if two matrices commute in one basis, then they commute in any basis. That is, the commutator of our initial bases indicated with E equals 0, then the final bases also equals 0 in the commutator relation. And the author gave us a hint, use equation A64. So, pretty straightforward, pretty short video, let's dive in. So what we're trying to showcase here is bases independence. And to demonstrate the commutativity of two normal matrices as bases independent, let us consider the following proposition. The one that we were given with, where with our initial bases, the commutator in expanded form equals 0. So taking a similarity transform, A64 of the commutator, well, we see that if we take the transform on both sides, and then on 0, we end up with 0 again. So this should already tell you enough, but now we need to see how these matrices transform under the similarity transform. As such, we're going to focus on this left-hand side only, since our right-hand side is kind of boring. That being said, we take the similarity transform of the commutator, expand the commutator, distribute the S and S inverse to each product here, as we see there. But we know that thanks to the identity matrix, we could shove that right in between T1 and T2 and T2 and T1, and things remain unchanged. Now, from putting that identity in there, we see that we could substitute in the fact that S has an invertible matrix S inverse that form this identity to happen. So now with the identity put in there, realizing that it doesn't affect the product, we can now input the S inverse S. Using associativity, we can shift the curly brackets from the identity curls into each triple product here. And what we realize here is that this triple product, and so forth on here, leads to the transformed bases matrices. So this similarity transform is pretty straightforward to apply, but also easy to show. Now that we have this and we've simplified the left-hand side of the equation, we can substitute this result back into our second equation up top, and this yields that we have this transformed relation of products equals 0. But this is a statement of commutativity, so we can write that as the commutator bracket, and just as we suspected, that equals 0, and we're good to go. Regardless of whatever bases, so long as there's a similarity transform to get us from one to the other, then we show that we commute regardless of the bases. Pretty darn cool. So quick video, but one that's very important to us because sometimes shifting our perspective gained us valuable insight. When we think about multivariable calculus, where we shifted from Cartesian coordinates to spherical coordinates, makes our life a whole lot easier. So very nice to see. If this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I also want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in supporting the channel and joining our Patreon community, you can check the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.